I'd like you to focus for just a minute on this graphic. Look at the three axes: volume of soil water content, mass soil water content with the units of measurement for each, and these are being plotted against the soil water potential measured on two scales, one in bars or atmospheres of negative soil water potential, the other one in negative kilopascals. These will both be negative numbers, but if we look at any given value, we can see that the bar or atmosphere is 1/100th of the kilopascal as a unit of measurement. I prefer to use bars or atmospheres of soil moisture potential, but in some measuring or monitoring devices, they will be using kilopascals or they'll be using centibars. And a centibar is 1/100th of a bar, so that would be equivalent to the kilopascal, or would be a measurement of that. Okay, if we use the bars or atmospheres of negative potential, what we're basically saying is we're comparing three soils here: a sandy or coarse textured soil with a medium or loamy textured soil, and comparing that to a clay or very fine textured soil. I'm not particularly concerned at this point in time. There are two lines for each one of these soil textural groups, one for a well-structured soil and one for a poorly structured soil. The biggest thing, the difference between these two for any given soil textural class is that obviously in a poorly structured soil, if we take clay as an example, the total amount of water being held at field capacity is less than in that same soil textural group where we have good structure. And that would be true for each of the textural groupings here, the loam and the sand as well. So kind of not being too concerned about well-structured versus poorly structured for a given textural class, but just the relationship between these three textural groupings, coarse being down here, medium being in the center, and fine being up here. Earlier we looked at how we measure soil moisture content. We had the gravimetric method, which is illustrated here on the right-hand axis. Mass soil water content, grams of water per 100 grams of dry soil. And over here we have the volume soil water content, which is meters cubed of water per meter cubed of soil. So you can see that those units are a little bit different, and when we did this one, we measured inches of water per foot of profile, since that's a numerical value that we're more familiar to work with, rather than meters cubed per cubic meter of soil. In our first initial interpretation of this particular graphic, one of the things that we should pick up on is that obviously at field capacity, or the maximum amount of water the soil can hold against the pull of gravity, which is a value of about minus 0.1 bar or atmosphere, we have the sandy soil holding considerably less water than the medium or loam textured soil, and that holding correspondingly less amount of total water than the clay or fine textured soil. In all cases, as soil water potential increases or becomes a larger negative number, we are losing water content from the soil, irregardless of whether it's coarse, medium, or fine textured soil. So the best thing we can use this graphic to illustrate is what type of soil moisture is remaining at a given soil moisture value or soil water potential value. Now, I indicated earlier, 0.1 bar or atmosphere is approximately field capacity. As we progress down below that to minus 1 bar or atmosphere, we can see that the sandy soil is not holding very much water at this content, at this soil water potential value. The loam soil is holding an intermediate amount, and then of course the finer clay textured soil is holding the most total water at that soil water potential value. Minus 1 bar or atmosphere is a soil that still has a lot of usable water in the soil profile. This is a very high value, meaning it's not a large negative number. At what point in time do we start reaching drought deficiency or water deficiency deficit value for plants? It will vary from one plant type to another, but usually somewhere around this minus 10. Minus 10 bars or atmospheres is a fairly representative value that most of our crop plants, at least, can take water out of the soil profile without significantly damaging their yield or yield potential. Grasses in general are much more efficient at that than our broadleaf plants. Fibrous rooted plants are more efficient than our tap-rooted types of plants. But at this level of minus 10 bars or atmospheres of soil water potential, now remember, everything's going into that value. It's a combination of gravitational matrix and osmotic potentials. I think you can see that if we increase the salt content of the soil for a given soil at a given water content, this value would become a larger negative number because the osmotic potential would be an additive factor. So soils, textural classes of soil, given the same textural class, if you have a soil that has a high salinity or salt content, it has a tendency to be more drouthy because plants will have a more difficult time withdrawing moisture from that soil. At minus 100 bars or atmospheres, there is very, very little water left in the soil profile that plants are able to utilize. Most of our crop plants would not be able to utilize water down to this level. Some of our most water use efficient plants, some that we might be familiar with, like Russian thistle and puncture vine and some of those types of plants, can survive and utilize water from soils down to this level. But you see the actual amount of usable water held between minus 10 and minus 100 is not a large amount on either a gravimetric basis or a volumetric basis, either one. Not nearly as much as the amount of water that's in that profile between the minus 0.1 bar or atmosphere and the minus 1 value. There's a much greater quantity of water here than as we get down to minus 0.1, or excuse me, minus 10 bars or atmospheres down to minus 100. So for all practical purposes, the level of water being held between 0.1 and on this graph about minus 10 is really our usable water that's being stored in that soil, plant usable water. So soil water potential becomes a larger negative number as the water content of the soil decreases. The next concept that I wish to discuss with you deals with soil water flow. We've been looking at the retention of water in the soil and the factors that affect retention, and we've alluded to some of the things which affect the flow of the water through the soil profile.